Hi everyone, it's Miss Wong here, and I'll be going over the velocity versus time graphs practice 1. So this practice actually has two graphs, but I'll be splitting the videos into two separate videos as each graph takes a little bit extra explanation, so it might be a little bit long for you to find the pause and stop between each graph, so I thought I would just split it into two separate videos. So this first question here is a ball rolls down an incline to a floor, then up a second incline. It stops for an instant, then rolls back down the incline. So this question gives you a bunch of table values that you must plot into this graph. After plotting it into the graph, you'll get lines like this. Okay, these distinct lines will be straight in characteristics, and each line will give us different phases. So you'll notice again that different practice that I post will either have the word phases, section, segments. They all mean the same thing. What are the different types of motions that you see on the graph? So the first question is asking us how many phases or sections or segments are there to the motion of the ball that's illustrated by this graph. So once you plug in all these values, you're going to get the same characteristics as I did for these lines, okay? You're going to notice that there's actually 4 different phases, okay? So the answer to question 1 would be 4. And the 4 different phases, we're going to talk about it a little bit more in depth. So section 1 here, you can see that this is an independent phase because of its straight diagonal line that's moving upwards away from that x-axis. Okay? It's moving away from the x-axis. It's straight, it's diagonal, therefore we know that every time we calculate for the slope of this line, we will get a constant acceleration. So notice here that I say acceleration because we're working with a velocity versus time graph. We're not working with a position versus time graph where the slope gives us velocity. We're working with a velocity versus time graph, and the slope will give us acceleration. So a straight slope such as S1 here will give us a constant acceleration. Constant meaning it's uniform. Meaning that if you pick any one of these points on this graph and plug it into that slope formula that you'll see in a bit, you can choose between these points here or the entire points here or these points here, you're going to get a slope or an acceleration that is the same. No matter which value you use to plug into that formula, you're going to get the acceleration to be the same number, okay? You're going to see that in just a bit. I'm just going to erase this here. Now let's talk about S2. S2 is a flat horizontal line. That's why we named it as a different type of motion. Therefore, that's the second phase part of our graph. It's a flat horizontal line, and we know that flat lines usually equal 0. Well, 0 what? 0 acceleration, because now the slopes or any of these lines that we see are going to give us acceleration. We see that we are not increasing in speed or decreasing in speed, so we're not accelerating or decelerating. We're staying at that flat horizontal line, and during this period of time between 4 and 6 seconds, we notice that we stay at 3.2 velocity. So that's giving us 0 acceleration. We're going to constantly be driving for 3.2 meters per second. Therefore, that horizontal line just means 0 acceleration, but it also means constant velocity. So you have a constant velocity because you're constantly at 3.2 meters per second. You're not increasing or decreasing. So let's look at segment 3 here, or phase number 3. It is going downwards, and we'll see that it looks like it's mirroring section number 1, and therefore our slope looks almost the exact same as the slope for S1. So when we calculate our values later, we're going to notice that they might be the same, and that's how you can check your work. So S3 is going downwards, okay, towards negative values, towards the x-axis. So we're going to expect to calculate an acceleration that is negative. Right here, as this straight diagonal line goes straight down and past the 0 on the x-axis, we consider that as a separate motion now because you're entering those negative velocities. Sorry, these are all negative velocities. It just got erased here. These are all negative velocities that we're entering. Therefore, we consider it as a separate motion. We're moving backwards compared to S3. Okay, where we are decelerating, yes, and we're still decelerating in S4 because we're heading into those negative values, and it's part of the same line. So later on, when we're calculating for acceleration of the slope for S4, we're going to see that it's going to be the same number as S3. So let's see what our next question is. Explain what is happening during each phase in terms of uniform motion or non-uniform motion. So there's either constant velocity or that acceleration. So S1, we talked about it already. S1 was a flat, straight diagonal line going upwards. So it's going to be a positive constant acceleration, meaning it is uniform, meaning any points that we take to enter into our formula will give us the same acceleration. S2, we talked about it as well. It's that flat horizontal line, and that means constant velocity because we're at the same constant velocity of 3.2 meters per second. We're not increasing our speed or decreasing it, so it's constant velocity. So uniform motion. And we have 0 acceleration because we're not changing our speed. Okay? S3, we have, again, a straight line, but it's going downwards. So we know it's going to be a negative, but it's still going to be a constant / uniform acceleration. But since it's negative, it's most likely going to be deceleration. You're losing that speed. Deceleration. Okay? Next is S4. It's part of the same line, so therefore it is a constant acceleration. It's going to be in the negatives because it's going to those negative values. And now we're going to do question 3, calculate the accelerations. Solve for this directly on the graph, just meaning that they want you to put it in this space here. Usually I would prefer if you wrote your answers on like a blank section of your paper so I can see the values better, but we'll just do it on the graph here because they want us to. But if you have space like over here, write it over here so I can see clearly, which I'll do. I'll do S1 here, and then once I run out of room, I'll go into the graph here. So S1, the acceleration, I'm putting an arrow on top because acceleration is a vector quantity and it has both magnitude and direction, equals, so we're looking for slope, it's rise over run, which is going to be rise is the y-axis, which is our velocity, so the change in velocity, over our run, which is the x-axis, is our change in time. So VF minus VI over TF minus TI. And we notice that this formula looks like the velocity formula because it is. We're solving for its slope. So it's going to be the same, just different letters, okay? Because we're entering different values and different quantities to solve for different other quantities. Like in velocity versus time graphs, we are solving for acceleration. So let's go into our graph and choose our final and initial values. I'm going to choose points on this graph that are for sure 100% those points. And you can look and grab those points either from your table, but we can see in the graph that at S1, we're going to choose a final speed right here because it's at that intersection. I know for sure it's going to be 3.2 and 4. I don't have to make guesses and have more decimals that it's going to be 2.8 0.85 or something like that. Let's use values that we're 100% certain of. Same with our T initial and D initial. We're going to choose this value here, 0 and 0, because we know it's for sure. We can do that because it's a straight diagonal line. Any points that we choose for this line to solve for slope will give us the same number. It would be different if we solve for a curved line, where we can, if we choose points here or here, it's going to be accelerating at different speeds. So these will all have different accelerations. However, it's different for a straight line. It's all going to have the same constant acceleration. So this is non-uniform, whereas this is uniform. For non-uniform, you're going to be making triangles and solving for that tangent. But we're not looking at that example today. So let's go back to our question, S1. So we know which values we're going to plug in. I'm going to write them down here. You can rewind and look back at your values as well. So our VF is 3.2 meters per second. Practice writing the entire units so that you can see at the end once you solve for your units. VI is 0 meters per second, and over time, which is TF, was at 4 seconds minus 0 seconds, and then 3.2 minus 0, you get 3.2 meters per second over times of 4 seconds, and you're going to get a value of 0 meters per second squared. 0.8 meters per second squared. Can't forget the 8, because once you 3.2 divided by 4 gets you 0.8, okay? It's a positive value. So if we can go back to our graph here, we notice that S1 is going in a positive direction. It's going away from that x-axis, and we did calculate a positive 0.8 meters per second. That's really good. Look at that unit. It's squared. It's for acceleration. We're not solving for velocity where it wouldn't be squared. So acceleration units, meters per second squared. Even if you had km per hour, it would be squared to show that it's acceleration. You can see that with the units, because meters per second squared here divided by another seconds, you're multiplying these seconds, therefore it becomes squared. Okay? That's how you solve for your units. All right, let's go into example S2. Acceleration over time, VF minus VI, TF minus TI. We're going to enter our for sure values. So I'm going to use points that are at these intersections so I don't have to guess decimal places. And these intersections are at 3.2 here and 3.2 here. For our time, it's 4 seconds and 6 seconds. So we're going to plug that in, and make sure you plug in the right values for VF and VI. So we have 3.2 meters per second minus 3.2 meters per second, because it's that horizontal line. Its velocity is constant. It hasn't changed. TF was 4 seconds. Sorry. It was 3 seconds. It was 6 seconds, 6 seconds, and then our TI was 4 seconds. So 3.2 meters per second minus 3.2 meters per second, you get 0 meters per second. And you're going to be dividing it by that time. So 6 seconds minus 4 seconds equal 2 seconds. However, when you take 0 divided by any number, you're going to get 0. Look at your values. Meters per second divided by seconds is meters per second squared. Again, the units for acceleration is meters per second squared. Even though you got 0, you still got to show those units. So 0 meters per second squared, which is what we guess would happen for acceleration, that you're going to get 0 acceleration with a flat horizontal line. So far, so good. Let's calculate for S3. So S3, sorry I stumbled over there with the 6 seconds and 3 seconds. The librarian walked in and I was like, oh, hi. And then, yeah, anyway. Side note, 3 seconds. Acceleration equals change in v over change in t equals vf minus vi over tf minus ti. Let's plug in our values. Again, S3 has constant acceleration, so no matter which points we use to plug into that formula, we're going to get the same acceleration, okay? So no matter which starting and initial and final values you choose, you'll get the same acceleration. Might as well choose values that you know are for sure at certain intersections, so it'll be easier for us. 0 is for sure going to be 1 for TF and DF, and for TI and DI, this point right here will be for sure as well because it's at that main intersection. So let's plug in those values. So we have 0 meters per second as the as the final, minus 3.2 meters per second over a time of 9 seconds minus 6 seconds. We get negative 3.2 meters per second divided by, this should be a 5 here, 5 seconds. Okay, divided by 4 seconds, you're going to get negative 0.8 meters per second squared. Alrighty, so if we look back at our answer for S1, we notice that it's 0.8 meters per second squared. We guessed that it was going to mirror to be the exact same because the slopes look like the exact same thing. They were using the same values, and if you look back here, there is symmetry. The slopes are mirroring each other, therefore the value of the slope will be the same. It's just the direction of the slope. Whereas S1 was positive, S3 is going towards the x-axis and into those negative values. Therefore, that acceleration will be negative, which we saw in our calculation, negative 0.8 meters per second squared. Right on. So far, so good. We also predicted, moving on to the next one, S4 to have the same acceleration as S3. So S4 acceleration, change in v over change in t, vf minus vi over tf minus ti. You're going to plug in those values, and we're going to use the for sure values that are given and not going to guess at these intersections because, again, this line is coming from S3. It's straight, it's a diagonal line, therefore it's constant acceleration, so we can use any points on the graph to solve for the slope. So we're going to use the most obvious points so it's easier for us. We're not guessing decimal places. All right, so I'm going to enter the values of negative 1.6 meters per second minus 0 meters per second, and then you're going to get 11 seconds minus 9 seconds, which equals minus 1.6 meters per second divided by 2 seconds, and you're going to get minus 0.8 meters per second squared. Alrighty, so we answered it, okay? S3 is indeed the same acceleration as S4. It's part of that same line going down into the negative values, so therefore we expect that when we solve for acceleration of both those lines, it's going to be the same. Alright, so we did that question. Let's see question 4. What changed direction? The velocity, the acceleration, or both? Both. Okay, why both? Well, velocity changed negative right here at segment 4. Okay, it changed negative at segment 4, and then acceleration changed negative at segment 3 and segment 4. Segment 3 and segment 4. And you can see that with the accelerations you calculated and which values are negative. When is the velocity negative? Well, this answer and question are the same as question 4. So S4 shows you that you're working with those negative velocity values, okay? And then here, when is the acceleration negative? We talked about it. It's negative at S3 and S4. All right, so practice this question. Slow down whichever points that you need slowing down at. Good luck, everybody. I am going to record the next graph in a separate YouTube video. So have a wonderful day, everybody.